I'm one of the coordinators of the series, along with Dane Scott, who is the director of the Center for Ethics, Dane. And Lori Young is another coordinator, the director of the Wilderness Institute, and instructor for this course. We also have support from the Dana Gallery, who has generously donated artwork for our nice poster that you see around campus and around town, and also for the weekly flyers. Next week, we also would love for you all to come back. We're experimenting with our first video conference. Mary Wood, who's a law professor from the University of Oregon, will be here on the screen broadcasting her talk live in an interactive form. It's a way for us to bring speakers to this audience without having to use so much carbon in her transport here. It's a new thing for us, so please come and participate, and we want to refine that for future years. Okay, I think that's all for the announcements. Now on to Dan Fagre. Dan comes to us from, as I said, Glacier National Park. He's been out there for 16 years directing research to find out how climate change is affecting our mountain ecosystems in Glacier, in the crown of the continent, and also to national parks across the country. He works collaboratively with a lot of other scientists. He said something about being kind of a ringleader for scientists that bring all these ideas and this research together. He's incredibly effective as well as bringing that information to public audiences and to public policymakers. It's not often that we have scientists who are such effective communicators and choose to spend their time communicating about these important issues. I think we're all really thirsty to hear about what are the impacts of climate change, and then to hear from someone like Dan who can communicate that in such an effective way. I first met Dan last summer when I took a group of students through Glacier National Park by bicycle, and I asked Dan to take some time talking to students. Not only did he do this, but he took a Saturday to do this. He spent 3 hours with us, brought his staff in, other managers from Glacier, other scientists, and we had this great discussion that showed me how much knowledge he had about the nuances of climate change, how they're affecting our mountain ecosystems, our water resources, and what that means for us as a society, and how we might adapt and respond to that. It wasn't 2 months later that I picked up a Backpacker magazine. I don't know why it caught my eye, but there was an issue in the fall about global warming. Opened up, who did I see there but a full picture of Dan Fagre there, story about his work and about climate change. So he's getting out there to many different audiences to talk about this. Just today, I looked him up, I Googled him, I saw there's a video on YouTube that you're welcome to go see through Backpacker magazine. His words are out there and his images are out there as well. I told him I put a plug in for a couple of books that he has out. One was published in 2005 on national parks and protected areas. Another one just came out last year on the crown of the continent on sustaining Rocky Mountain landscapes. So please welcome me in welcoming Dan Fagre here, and thank you so much for taking your time.
Well, thank you very much. Because I am from West Glacier, my carbon footprint wasn't too large getting down here. I drove an old Subaru, so doing what we can. Now, behind me here is the view from near my office in Glacier National Park, a very wintry and rather Arctic-looking scene. And in fact, this is my office, the back door. You can see what I do for exercise. And it's scenes like this that make a lot of people in Montana think, well, maybe climate change and global warming isn't such a bad deal after all. In fact, these disgruntled individuals that you can see are doing the annual meeting of Montanans for global warming. And there's a lot of people that like to do a little less shoveling and snow blowing and everything else. Unfortunately, these Montanans and all of us are going to get more than we bargained for. Just because it seems that the warming might have some positive impacts does not mean that it also doesn't have some profound capabilities for changing our ecosystems and the way that we live in this landscape. Now, the crown of the continent, I think most of you already know, is an area that has got Glacier National Park at its center and encompasses a Bob Marshall Wilderness area and goes up by various definitions well into Canada. It's a transboundary concept. It's a fairly intact mountain system. And this is an international treasure. This is a relatively pristine and fairly undeveloped area compared to other parts of the planet. And that's one of the reasons that's an excellent area to look at climate change, many of whose impacts are subtle. And so you need a place that's natural, that has all its parts, and that is responding primarily to a climate change signal, rather than other kinds of man-caused impacts that might confuse that signal. So basically, you might view it as a recreational area. We look at it as a darn good laboratory. Now, it's a beautiful laboratory nonetheless. But a lot of people ask, well, why mountains? Why are you studying mountains? They're a long ways away. There's usually not a population center there. But it turns out that on a global scale, mountains like this are vital to human existence. About 50% of the water that humans consume globally comes directly from mountains. That's the water for drinking, for municipal use, for irrigation and agriculture, for putting your canoe in, and everything else. And mountains are critical because they reach up in the atmosphere and they squeeze that moisture out and they deliver it to us. And so these mountains are very important even to people a long distance from them. Now, in the fairly arid North American West, that figure is even higher. It's 87%. So we are very, very dependent on water. The paradox then is that mountain landscapes like this, particularly high elevations, have experienced 3 times the climate change, the warming, that other areas have. And so like the Arctic and the Antarctic, they are uniquely sensitive to climate change. So here's a situation where we're very dependent on them, despite their long distances from our population centers and the sort of power bases where a lot of decisions are made about our western landscapes, and yet we're very dependent on them. Now, mountains are good for a lot of other things than just delivering water. Obviously, there are a lot of extractive resources here. They're important for biodiversity. They're often protected areas, for instance. And many of our national parks, in fact, encompass mountain areas. They're developed last, sometimes the least, and we're attached to them as Americans. National parks are a uniquely American idea. But here's the rub. This is the Many Glacier Hotel in the Many Glacier Valley of Glacier National Park, where there are not many glaciers anymore. Our national parks, our pristine protected areas are being affected, and our protections perhaps are not all that effective. Now, another thing, when you look at the morning commute for some of my employees here, is the fact that these are vital economic engines of growth. Glacier National Park, for instance, if you look in the background behind the skier, this little thin strip of road here going up the slope is the Going to the Sun Road. And in the spring, when that is still closed, the regional economy loses at least $2 million a day. Tourism, unbelievably, is the world's #1 economic activity. And I know it's true because I read it somewhere. But it underscores how important climate change will be able to affect all different parts of American society and global society as well. So you've got a mountain landscape, and you want to find some way of tracking how it's responding to climate change. Now, what you see behind me here is a map of the spatial distribution of climate. And all the bright colors on the eastern seaboard, basically east of the Mississippi there, all of those are contained in each one of those little mountain areas. So almost an entire continent where the climatic complexity is crammed into these mountain areas. And so it's very difficult to measure climate change. It's very difficult to predict weather in mountain landscapes. And so it poses quite a problem. And luckily, there's a solution that is ancient and is provided for us. And that's these small alpine glaciers, like you see above my head in this photo. This is Swift Current Glacier in Glacier Park. And little alpine glaciers offer a lot of advantages for being barometers of climate change. First of all, you can see them, unlike something like soil carbon, which is amorphous and distributed all over, hard to measure. Scientists argue about it a lot anyway. Secondly, you can get a GPS of the margin, you can photograph it, and they average the kind of snowfalls that we get from year to year over time, over decadal time scales. So that means if a glacier is retreating or is expanding, it means you do have some local climate change occurring. And of course, there's intuitive link. People get it when it warms up and ice melts. And of course, lastly, the advantage to glaciers, they can't adapt. They can only sit there and reflect climate, and so there's no partisan politics involved with glaciers. They don't vote, they just sit and melt. Now, glaciers are well distributed around the West, and so that makes them good for looking at climate change on bigger scales than just Glacier National Park. You'll see here that these are all ice bodies, permanent snow and ice bodies, many of which are big enough to be called glaciers. And they're all on federal land. Nobody owns one personally. No one has one in their backyard. And so these are ideal for observing the kinds of changes that we want to see. Now, Boulder Glacier in 1932 is pretty impressive. You can see some little tiny tourists there, dwarfed by that large ice cave. And you look at what happened in 56 years. Not only is that glacier gone, but vegetation has moved in to replace it. So it's a fairly radical change in a landscape that has been glaciated for a long time. Cheney Glacier is another one, and if you watch closely, you see how much that in turn has also melted. It's a mere remnant of its former self. This one, Boulder Glacier, used to be very, very impressive. You saw the ice cave in part of this, but if you look at the fact that it actually spread over the pass and was going down both sides of the mountains, the fact that this is all that's left is pretty daunting. And so this landscape is changing quite a bit. Grinnell Glacier, which a lot of you might have hiked to, sort of illustrates what happens when you can't drain away as you melt, and so you form a glacial lake in front of you, a proglacial lake. So Grinnell Glacier is basically melting into its own puddle. And you can see with the red line there that the ice elevation has gone down. So it's not like shrinking, if you look at it from space, it's also thinning quite dramatically. So you're looking at a dying glacier there. Now, we've compiled a lot of these, and you can go to this website here, the Repeat Photography website, download these, and do what you want with them. And these have been very effective in communicating the idea that climate change is important in this mountain landscape. And we've had these downloaded all over the world. And the typical kinds of things are school kids or newspapers, magazines. Have been on every major TV network, not only in the United States, but most of them around the world. But you do get some odd things like the book on aging. Why they put that in there, I don't know. Or, of course, the Italian fashion magazine. And we didn't really want to know what they're using it for. But this illustrates that what we see is sometimes more important than a lot of data. And so this has been fairly compelling. Well, that's what's happened at Glacier Park. What's happening around the West? If you look at the relative amount that these glaciers have shrunk all across the West, you see that we are not unique, we being Glacier National Park. This is a phenomenon that's occurring everywhere. Moreover, if you look at the Pacific Northwest, the gray blob in the upper portion, the drivers for the melt of those glaciers are not only warmer summers, but also warmer winters. And a lot of climate change is not so much that we get hotter, is that we get less cold. And this affects the glaciers directly. Now, I'm going to take a little divergence here to talk about surprises. We typically think of climate change as occurring gradually, even if it kind of speeds up. And we think about ecosystem responses being gradual in turn. So here's a typical cartoon of a climate boundary. The trees are surviving right up to that. The brush survives where it's too dry for the trees to be. And as the climate boundary moves, so do the plants. And so this is sort of the nice, tidy way that ecologists have looked at climate change and vegetation over long periods of time. And this sort of typifies it. What you see here is a map of the current distribution of 3 species of pinyon pine. And the red dots are where they started. And so this is a full glacial period ago. This is 25,000 years ago. And if you watch in the next few slides, you'll see how these plants gradually moved over thousands and thousands of years until they got to their present position. And so that's where they are now. And this kind of fits our models of gradual change. In fact, if you look at this, it took many, many tens of thousands of years for these plants to move across this landscape as climate changed. And 43 meters a year is not a whole lot. I mean, a tortoise can walk a lot faster than that. And so this has dominated our views of how climate change and ecosystem change occur. There is the assumption that they're both gradual, and the important thing is that from a management standpoint, if something's happening, you apply management, and if it's happening faster, you apply more of it faster. That's the management response. Well, here's the rub. if you look at the kind of natural variability that we've experienced in Earth's climate system for the past 500,000 years, you see all the ups and downs there with the temperature and the carbon dioxide in the atmosphere. So there's a lot of natural variability. It goes up and down, up and down, up and down. But if you look at the far right-hand side there, you see in 1800 where we were. And now if you look at what's happening, the thermometer is going up. And so we are departing from the natural variability by a very, very large amount. Now the temperature lags behind the carbon dioxide. So the fact that the carbon dioxide is higher than it's been for 650,000 years, possibly a million years ago, by direct measurement from bubbles in ice, or as some scientists think it's even longer, up to 24 million years ago, we've departed from the norm. This is not the kind of gradual change that you saw with tens of thousands of years for plants to move. This is something bigger, and it's something faster. In fact, if you look at this little cartoon, the amount of carbon dioxide in the atmosphere is only varied a little bit, the width of that kind of cloud, that worm of points there. And it's only gone between 180 parts per million, 280 parts per million, and we've moved back and forth between glacial and interglacial periods, on scales of 25 to 50,000 years. Back and forth, back and forth, back and forth, millions of years, millions of years, millions of years, and that's where we are today. Way outside the norm, and that's where we're headed. So clearly, we are departing from something that's been quote-unquote normal for up to millions of years. So how are ecosystems going to respond? Are they going to respond gradually? Well, here's a case in point. This is in the Southwest, and what you're seeing is the beginning of a massive forest die-off. All the brown canopies here, the pinyon trees, were suffering year after year after year with drought, 5, 6 years. Okay, and they're all hanging on because they're adapted to being, basically thirsty. But they all died on the same year. Virtually all of them hit their physiological maximum. They hit a threshold. And once that threshold was reached, you had profound changes occurring over thousands of square miles. And as far as we can tell, this hasn't happened in the Holocene, meaning the last 12,000 years. A threshold was crossed. A big, huge ecosystem change occurred in 1 year, not thousands of years. And in fact, this is a map showing all the areas where this has profoundly changed, and it's changed the hydrology, the erosion, and everything else. And of course, pinyons produce nuts that a lot of organisms eat. And so you had a massive conversion of an ecosystem in 1 year. Now, the importance of thresholds, and you can look at these bullet points real quickly, but the big thing is they're nasty surprises. And they come on us very quickly, and we don't have the adaptive capacity, we don't have the management. In fact, we don't even understand them. So they're big surprises. And a threshold is something where you have incremental change, bits and bits of change, things respond a little bit, and then the last little bit of change creates a whole new dynamic. Things go off in an entirely different direction. So again, looking very, very briefly at this little graphic, this is our view of gradual change. We don't know how fast it's going to be, so there's 3 different lines, there are different slopes. And when the bad effect comes, the impact, you can see that the faster it's occurring, the sooner you're going to have to deal with the problem. Okay, that makes a lot of sense. But what happens if you have a threshold? You suddenly have a deflection in that gradual change. It changes trajectory. You've got a big problem a lot faster than you would have thought. And of course, we don't know much about them, so we don't know where they are, and of course, we don't know their rates. All we know is that they really mess up our view of the gradual world and our management responses to it. Now, if you're a fisheries manager, here's a case in point. Big surprise. You can see that things went along with some variability for a long time. Bam, all of a sudden you had some threshold cross, you had a huge growth and a complete crash. And so in 1992, you didn't have any fish to manage. A big threshold was crossed. This is not the way we like to view our world. It's not the way we like to view how our management responses will be. Now, across the West, you had a lot of really, really mesic, wet-loving trees get started during cooler and wetter periods. And they survive because they're in these little pockets that they can protect. They can self-regulate the local climate. And so we have these treasures like 5 to 600 year old massive trees like this that have been there a very, very long time. But what happens when we start getting more frequent fires and we convert those old growth forests? What happens when that climate envelope has long since left the area and is somewhere else? What we get back in many cases is lodgepole. And some people have called these biological deserts, although if you're certain kinds of species, maybe that's not true. But clearly, you have a completely different kind of forest that could potentially take over large parts of the United States because the climate has changed and the trees that were originally there can no longer come back. The climate change thresholds have been crossed. And here's one of the organisms that's liking the lodgepole. These pine beetles, for instance, are now at the point where the winters are not cold enough to kill the populations or to greatly reduce them. So you have a bigger population every spring. Much, much better overwinter survival. And then it turns out that when you cross a temperature threshold, they can reproduce twice a year, not once a year. There's your surprise. There's your deflection upward. That's the threshold that's crossed. And the concern that is being expressed pretty widely by a lot of forest entomologists is that you've got a northward spread of these. In fact, British Columbia had a 3 million acre outbreak, 3 times the size of Glacier National Park last year. Enormous and quite devastating. But what happens if you go further north and you connect with the boreal forest and you can jump to jack pine or something like that? These beetles could move across the continent and they could move south. And a lot of our pulpwood comes from pine plantations in the southeast. And this would be not only ecologically devastating, but economically devastating if, as some forest entomologists think, this threshold once crossed, you can't reel it back in. You've got a new reality to deal with. And this is a little bit what that reality looks like. It's not so attractive, but it also creates some fears about huge fuel loads and catastrophic fires as well. So what about a little bit north? This is just an animation of the Arctic sea ice disappearing during the course of a summer. And as many of you know from the news, this past year was the smallest extent of sea ice ever recorded. It's been a continual trend, but they were pretty shocked to see it go to this extent. In fact, one of the recurring themes about climate change is things are happening faster than we thought. This simply represents a model with the blue area being the uncertainty involved in that, about how quickly that sea ice would go away. The red line, unfortunately, is where we are. Not only did we miss our guess on this, we missed it by a whole lot. We exceeded the statistical bounds of probability as to how quickly this would go away. So kind of a surprise. Now, if you look at the Arctic sea ice here between 1980 and 2007, you can see very quickly that it's a lot smaller in 2007. And here we're simply looking at the same contrast, but if you look at the points where the ice no longer contacts the land, all these little red blobs are places where you used to be able to get out on the ice, and you can't anymore. And this is the fellow that is going to be impacted by that. A threshold is crossed wherein they can't get out to the ice. It's too far. They have some amazing survival capacities, but the threshold's crossed. And so now they're expecting that you would see all of Alaska's polar bears eliminated by 2030, and 2/3 of all the polar bears worldwide gone about the same time. A threshold's crossed. So further south in a warmer climate, the corals. We've heard a lot about them. They're threatened by a lot of things. And here you can see in the lower right panel a coral where half of it's bleached and half of it is still alive. And so basically when you get high enough temperatures, the symbiotic algae leave and it looks white. They call it bleaching. And usually they recover. And this is something that they're adapted to experiencing periodically. But when a threshold is crossed in these 3 panels, you can see that once you get about 2 degrees C warmer waters, you go into a fatal nosedive. And so the panel C there shows basically coral death from which you cannot recover. So there's a threshold that's very clear and fairly well understood compared to other kinds of systems. And so you can look at the kinds of impacts in the text in the bottom as to what happens. And of course, as it turns out, there's a lot of other organisms dependent on that, and there are a lot of human endeavors that are dependent on it too. So to track this, they've been looking at the thermal heating weeks and looking at the thermal stress in corals. And if you look back here at 1985 and you watch in the bottom, you see the pink line going up and down with the different temperature spikes. And the purple areas indicate a little bit of stress. But as you watch this animation go forward in time, you can see that a threshold is approaching. Here's the first indication of it when they'd never seen that much thermal stress in corals before. They started worrying about it, they started doing more monitoring, and then in the past 2 years, they've had the most massive coral response to temperatures ever. And so in this last panel, you see pretty much from a coral standpoint, ground zero. And so we are starting to have some significant die-offs of corals on a global scale. It's not just confined to the Caribbean. So then you get these kinds of grim statistics, 42% dead, 96% bleached, and so forth, going throughout this area. And if you look at the temperature increase through time, you can see we are currently, in that orange bar there, crossing the threshold right now. As we understand corals, and with recent data, this is not modeling, this is not projecting, this is not theoretical, this is just measuring. And you can see we're measuring the fact that we're crossing that threshold, and as you go forward in the future, you can see the two options with the dead coral and the live coral. Another quick aside is that in addition to temperatures, which is a big enough problem for corals, you also have the fact that the CO2 in the atmosphere is going into solution in the oceans. And they thought, well, we'll be able to measure this in the future. Again, that recurring theme, it's happening faster than we thought. This is where it actually is. Scientists were shocked to find that they could start measuring the acidification of the ocean 20 years or more before they thought they would be able to. And that slope, that yellow slope, shows you how well you can calcify, how well you can create coral and the subsequent coral reefs. And as we go forward, you see that we get down to that threshold, which is based just on the chemical content of the ocean water. And so if you have both the thermal stress and this stress, the corals get a double whammy. Well, if we take these lessons back to the crown of the continent then, the idea that there are these thresholds, we can look very quickly at our glaciers again, and wherever you go in the park, you see these little panels showing that it's the same story all over. And in 1910, when the park was founded, we had roughly 150 glaciers in the park. We now have somewhere between 20 and 24 glaciers remaining. The vast majority of them are gone. Moreover, if you look at larger glaciers like Sperry, they're about 24% of the area that they used to be. And these are glaciers that have been on this landscape for a minimum of 8,000 years. So there's something big going on there, and we decided we better get out and measure these before they're all gone. So from space, you can't always tell what's rock and what's ice. And if you look at the rock on the right side here, you can see that that might be misinterpreted as ice. So we walk the margins with a global positioning system and get very precise measurements. In fact, I like to joke that with current GPS, we can get more precise measurement about where that ice is than that glacier is going to actually be by the time we hike out and download it and put it into our GIS and make the map. The glacier's already changed on us. In fact, this GIS representation of Sperry shows in the blue what melted in just a few years. So these GPS measurements are confirming what we've seen from space and from aerial photography. We also go out to that proglacial lake with the Grinnell Glacier that you saw before. We backpack these boats up there. You can see the GPS unit on the woman's back there. And we go right along the margin and get that measurement. Again, it can sometimes be fairly dramatic. If you look at this aerial shot of Grinnell, you see the point jutting out into the lake and two big cracks behind it. And most of the time, we're used to gradual change. Here's a threshold. That huge chunk of about 5 acres broke off all at once. And it disintegrated into lots of little icebergs, and the blue line is what was left. A lot of the white, just to the upside in the picture of the blue line, is actually disintegrated icebergs that blew back. I bet you didn't know icebergs blow around. This represents just 2 years of melt, and it represents 9% of the area. So if 9% of this glacier goes away in 2 years, how long is it going to be there? We also look at the thickness. Here we are using an ice radar, shoots a signal through the ice, bounces up, we see how deep it is and so forth, and we get this view of how thick the ice is, so we know, how much longer it has. And you can see the thinner areas in the lighter colors, and those are the areas that are going to go away very, very quickly. In fact, some of those areas are so thin that when I took an ABC crew out there, the photographer got up on summit and he broke off part of the glacier. So we didn't tell the rangers. But we also have to measure how deep that lake is. And we're not NASA, so this is what we do. And you'll note the duct tape, always a very important part of science. And so we duct tape some paddles together, fish finder, a GPS, and a somewhat willing volunteer. Given that this water is 32 degrees and just a hair above, it's barely liquid. It's a very, very cold task. And even with the wetsuit on, it was very cold. And of course, we realized that as we sent him out there, even small glaciers kind of dwarf human beings. And as he got out there further and further, we realized that we could barely see him. And we also noted that these icebergs that were drifting in the lake were blowing around the wind very, very gradually, but they actually pinned him in several times. And so he had to wait till they drifted apart before he came out. So he wasn't willing to do that a second day. But that's the kind of survey that he had as he got chased around by the icebergs. But when you put that into a GIS and you find out how deep that lake is, it's surprisingly deep, about 187 feet deep. So if you add up the volume that's in the lake, you add up the volume of the ice that remains, you take the historical counts that show that it was 1,000 feet high when they first discovered it, you look at where the ice was up on the cliffs, and you put that all together and then get out your envelope and do the back of the envelope calculation, another major part of science, you find that 90% of Grinnell Glacier is gone. Only 10% of that ice that's been there for thousands of years is left. And this looks like the punishment pit, but actually it's science too. And we have to dig a pit all the way through the annual snow, so this is in the spring, and the woman at the bottom is standing on the surface of the ice. And this is not, champagne powder snow. This stuff is denser than snow cones. It feels like concrete bricks when you're digging in it. It's very spongy, takes 2 people all day to dig this, and it's up to 30 feet deep. Now I bring up that point because what happens is you have to melt all of that in the summer before you start melting the glacial ice itself. And so here we are seeking enlightenment at the end of the summer by going up and finding our ablation stakes. And here you have an example as these segmented stakes have been drilled through the ice. As the ice elevation drops, they fall over so they don't snap in the wind and so forth, and grizzly bears don't get attracted to them or something. And everything that is being shown there has already melted. And this is one of your campus professors, Joel and Blaze, that are looking at the sad statistical facts here on the ice. Now, all of that 30 feet of snow melts. Then 1.7 meters of ice is also lost, about 5 feet or more. And if you take the radar measurements for this glacier and find out it's about 40 meters deep, and you divide that by 1.7, all the math majors will already know the answer, it goes away in about 20 years. Now this is an animation of 2 of our largest glaciers in Glacier Park disappearing. And of course this is historical data up until we get to 2000. And one of the things to note is that if these are the 2 largest glaciers in the park, and you see what's happening to them, by inference a lot of the smaller ones will be gone much earlier. So right there in that panel at 2030, the glaciers in Glacier National Park are likely to be all gone. Now this model was put together with some different data in the 1990s. And as you know, we've been tromping around there, and particularly in the last few years when we've upped our monitoring of these glaciers, we've got new information. And if you look at the actual area for those 2 glaciers, Jackson and Blackfoot, in 1998 at 2.94 square kilometers, you'd see that according to the model, we should have had a lot more than that 2 years later in 2000. In fact, in 2010, 2 years hence, we're supposed to have almost the amount that we had back in 1998. So this clearly needs updating because it shows that we were too confident. We thought that we were projecting something that people would barely believe, and in fact, we were wrong. And the joke about models is they're all wrong. It's just some of them are useful. And in this case, what's useful is we realize that we're changing faster than we thought. So what are some of the cascading effects of glaciers going away? When the glaciers are gone, that has an impact on a lot of people, but it is in some respects, mostly about what it reflects in the rest of the ecosystem. But glaciers do provide meltwater. And this is a stream gauging station below Grinnell Glacier. And if you look at the hydrograph, the amount of water that runs out of the mountains all year long, glaciers are critical in keeping water in many of our streams late in the summer when the snowpack's gone, the soil moisture is gone, it's dry, the trees are evapotranspirating, and the aquatic system depends on getting some glacial meltwater. And so this shows you the basins in Glacier National Park that used to have glaciers in them, and you see they're one by one disappearing. And so now what we have left in Glacier National Park are many less basins with glaciers in them. And these little things that nobody buys postcards of and takes pictures of except us are at the base of the food chain. They're very important. And they are not only dependent on having some water, it has to be cold water. Each of these organisms has a very narrow range of temperature tolerance in the water. What's lethal for one is just barely cold enough or warm enough for another. So there's this replacement of species as you go from the cold glacier and the meltwater immediately coming out of it and go down through the stream bottoms and out into the plains. A steady replacement. And in this particular simulation, we look at what happens when Pompeii Glacier in the left panel disappears. And you can see that in the present glacial runoff, you have 3 species. But once that glacier is gone and the water warms up, one of the species can't survive there anymore. It's too warm. But it's hunky-dory time for another. The species that's yellow actually expands. So there's winners and losers in climate change. But in this particular case, it's going to affect the interactions between these species and the rest of them on up the food chain. In fact, if you look at bull trout, our native species that we're very concerned about, not only is this part of their prey base, they also directly need cold water. They've been called the polar bear of the aquatic species, the polar bear of trout, because they have to have that cold water. So not only is the water going to be warmer and their prey base has changed, their interactions with introduced species are likely to change as well. And this is a level of complication that's difficult to address. We don't know exactly what will happen, but we know that's not good for bull trout to be losing some of its habitat. Wade Friedenberg, a fish biologist in our area, has said that this perennial snowfield that's clinging to the cliff in the background is providing the cold water, making this adequate spawning terrain or territory for the bull trout. And when that particular snowfield is finally gone, he doesn't feel that bull trout will be able to spawn in this area again. And in fact, Bruce Ryman has done a little bit of a quick analysis, and looking at temperatures warming up and climbing up the mountainside, you find that in the upper panel where it's current, you have a lot of potential bull trout habitat. And as you can see, when it goes up 100 meters or 250 meters or ultimately 800 meters, you have a lot less habitat. The bull trout can't survive that warm water. So there's less habitat, but of equal importance, it's fragmented. Trout can't get to other basins now to find other suitable habitat. So the fragmentation is just as important, and that is a threshold that Bruce feels will be very, very critical in the future of bull trout. Now, snow is still king. Snow, in spite of all the warming, still dominates our landscape. And so we started to look at what snow is doing other than just melting and providing water for us all to drink. These are ribbon forests up in the Preston Park area of Glacier National Park. They're called ribbon forests because there's long linear strips of trees, and in between those are long linear strips of meadow. And the key part is that in those meadows you have a lot of biodiversity, you have a lot of forbs, you have a lot of food, basically, for wildlife. You don't see them out there eating the bark. This is where they're foraging. And so it's important that these meadows, these strips, stay open. And what's happening is that we're finding that trees, subalpine fir primarily, are invading these areas. In the foreground, you have small trees that are 25 to 60 years old. In the background, behind that magenta line, we've aged those trees, and they're all 250 to 600 years old. They don't look very big. It's tough environment up there, and so they're very, very old, even though they don't look very large. Now, the key thing is what happened for hundreds of years in between those two cohorts. What changed to allow trees to finally begin invading? And it was snow. The snowpacks have thinned. They're going earlier. The trees can get a start, and once they can get enough photosynthesis done and get established, they can poke above the snow and survive. But if they're under snow for a large part of the year, they basically drown. So snow has been very critical in keeping a lot of our upper alpine areas free. Here's another example below Pittamakan Pass, and if you see that red line, on the downhill side, mostly on the right, are the older trees. And everything on the uphill side and to the left primarily is all brand new. This is due to the warming climate and the change in snow that we've had at these high elevations. So what happens to alpine habitat for the iconic species like mountain goats? And of course we deliberately chose a cute young thing. You know, the big eyes, the whole works, and in the background are those evil trees coming to get them. Already we've had 4% of the area in our alpine zone taken over by trees. And of equal importance to just reducing the total habitat for organisms like this is that fragmentation. Once these trees cover passes, for instance, or ridge lines in between mountains, mountain goats are extremely vulnerable marching through forests to predators. That's why they're not there, or one of the many reasons. And so we may start having isolated populations of mountain goats, as well as less habitat for them in general. So this would be ironic, because the mountain goat, of course, is iconic of Glacier National Park. You see it on business logos and letterheads and all kinds of things. And the icon is being impacted by changing climate. Now, I told you earlier that Montanans are wishing for warmer weather, at least in that one slide, and they're getting it, by golly. If you look at the lower panel, this is the increase in temperature for Montana over the last 100 years. And the important part here is it's in lockstep with the entire northern hemisphere. We're not weird, we're not unique. We're doing what a lot of other places are. And the red dots in the map up there show you how much increase there is. The larger the red dot, the more it's warmed. And interestingly, in our area, the winter is warmed more than the summer. So it's that our winters are less cold more than that our summers are blazing hot. But we looked at thresholds. In this analysis, we thought, well, when you have frost, when you have freezing, a lot of plant processes shut down, a lot of biogeochemistry shuts down, and so that's a threshold. It's not just the average, it's how much time you spend above or below a threshold like freezing. And you can see here that we have many, many, many less days when it's freezing in western Montana. We looked at the flip side and said, well, how many days over 90 degrees is it when stomata shut down and a whole host of things happen, and people go into cool bars and drink a lot. And it turns out we're getting lots more 90-degree days. And that is also spread over a larger part of the year. In the left side, you see the span of time between the first day you hit 90 and the last day you hit 90. And by the time you get to the end, you see we have almost twice as long a period of time when we can experience 90-degree days. So we are, in fact, getting hotter even in the summer. It's just the winter is outpacing us. Now, if you look at the really big hot years with lots of 90-degree days in them, you'll see they line up pretty darn well with a lot of our big fires. And so a lot of our fires are becoming more frequent, and in some facetious way you can say that fighting fires is becoming more of a spectator event, as these guys are demonstrating. And part of the reason is that the fires are exhibiting fire behavior they haven't seen before. They're not sure how to deal with them. They're more dangerous. They're more ferocious and intense, move faster. And so fires have changed in the northern Rockies in particular, and this is very likely at least partially fueled by that hotter temperature. There's a lot of other factors as well. Well, you look at the winter part of it, and these are the trends in snowpack across the entire Northwest. All the red dots mean that you have less snow in terms of its water equivalent. So your snowpack is basically smaller on April 1st all across the West. And the bigger the dots, the smaller your snowpack, the greater the change from departure, in other words. In other words, we got less snow. And if you look at when that snow melts in the spring, the bigger the red dot, the earlier it is. And the red dot down below for scale is showing 20 days earlier. If you look at the size of some of those red dots, we have spring a month earlier than we used to in terms of snow melt. We just published, or we just submitted a paper, which we hope to get published, showing that the last really cold weather in western Montana used to be on average at the end of February. It's now moved on average to the end of January. So we have less winter, we have less snow, it's warmer, and we have more of this in Glacier Park. This is the aftermath of our increasing size and frequency of fires. In 2003, 13% of the park burned. On the west side of the park, since 1988, you've had a successive series of really, really big fires, some of which actually burned over previous burns. So the entire western side of the park has been dramatically impacted, and half of the park is at least 500,000 acres by these fires. These are threshold changes. We don't have forests like we used to. We have this kind of habitat, and again, there's winners and losers, but there's definitely a fundamental change. Now, something we often don't think about with climate change are snow avalanches. And we mostly think of snow avalanches in terms of not getting caught in them when we're skiing, hopefully not driving down the road when one rips off a ridge, and so forth and so on. But it turns out that they are not only key in infrastructure and all the kinds of things that we typically think of, they're also very, very important ecological agents. And so snow avalanches keep these chutes open. They come down and periodically scour the trees out, and what you get in its place then are all these forbs, all these wildlife foods that grow in their place. In fact, there's also some thought that having these fire breaks, natural fire breaks, changes the fire spread dynamics as well. So snow avalanches have a lot of impacts, and they bring nutrients from the ridge tops all the way down into the stream basins and actually change some of the stream chemistry and the dynamics of streams. So who would have thought? From the highest ridges, these snow avalanches are conduits of material and chemicals and changes in fire and a whole host of other things. And you can see here how green and lush some of those big avalanche paths are in the background in this particular picture. And so they're often called bear elevators. And the bears start foraging at the bottom because these are key foraging areas for them, as well as a host of other species. And so it'll be critical potentially for grizzly bear habitat as well. Now, an analysis of a paper that was just published in Arctic and Alpine Research was focused on one particular avalanche path, and a couple lessons. One is that you can read snow avalanches from trees. When trees get bonked by a snow avalanche, there's a bruise on the uphill side, and you see the fatter rings on the right side of the tree wedge here, and that's where the tree is trying to straighten itself up by growing more on that side. So you can tell when it got hit, you can tell the year, you can sort of infer the magnitude, and we find that trees are telling us that there's twice as many snow avalanches occurring in these mountains than records are showing us. Because, of course, a lot of them happen in the dead of night or on a foggy day where you don't see them, but the trees know because they get hit. And this is a probability map of how often snow avalanches impact this particular chute. And the key thing is that if you look in the upper portions, you see it's very frequent. In the deepest color, every 2.4 to 2.9 years, you get a major avalanche coming there and affecting trees. A regular disturbance that is very important to the ecology of this area. Now, look at that same path again. And what happens if you have lighter snowpacks, they melt earlier, and the snow characteristics change, so snow avalanches don't come down to the bottom like they used to, as in this slide, but start on average stopping higher and higher up the slope. Pretty soon, you don't have snow avalanche paths. You have a major change in the forest cover and the forest patterns from a climate change-induced cascading change on a whole series of ecosystem events that still winds up causing a big change. Now, the last thing about climate change and thresholds and surprises is that when we start getting more of our winter precipitation as rain and it falls on top of snow, you start getting a whole host of different things happening. One of them, of course, is you get some big floods, some big events. This is the 2006 November flood that ripped off a section of the Going the Sun Road and caused, I don't remember how many millions, 30 million or something like that, and tore up trails and bridges and all kinds of things. And again, it's kind of a threshold because you only have to warm up a little bit before the whole dynamic of snow in the mountains has changed. Once it's raining, you have a different dynamic. In fact, there's some evidence that these mountains that are always shattering and falling apart anyway have had a lot of this loose rock glued to them by permafrost. And as that melts, you have these SUV-sized rocks coming down and impaling themselves on the sun road that you just fixed. So it's way annoying to the road maintenance people. It's also dangerous. And so, next time you drive that road, keep a watch up slope. You may see something coming at you. Now, these are the kinds of thresholds that can change many of the functions in this ecosystem in the Northern Rockies and the Crown of the Continent area. I've talked about all these points. I just put them up here so you can, take a brief snooze. The impacts, though, are profound. I mean, it's kind of a litany, a kind of a list of these things, but together they can change a lot of what's happening. So what about solutions? You know, I mean, I've given you a lot of bad news. And you know, you might want to lay on a railroad track and wait for the train to come by. But there are reasons to get after it. The first thing is, what is needed in research? Well, managing for resilience is kind of a, you know, soppy sounding sort of thing to do, but we don't know exactly how to do it, but we know it's good. And so we need a lot more research on managing for resilience to climate change, or to improve the ability of the system to adapt to these thresholds and to these cascading changes. We need a lot of early indicators, early warning systems. I mean, a lot of times we're not getting after things until after they've happened. So we need to try to find some things that give us hints that the system is about to go through a major flux. We also don't know how to fix ecosystems all that well, and we don't know how much time we have after a threshold is crossed to do that. So these are all some very, very clear research needs. Another one is, and this sounds really boneheaded simple, but you know people, we don't talk to each other. And one of the things researchers are now actively doing is talking across mountain systems, and the same things are happening in Switzerland, same things are happening in the Himalayas, same things are happening in the Andes. In fact, they're happening faster in a lot of those places. Switzerland may lose all its glaciers in the entire country by 2030. You know, so what happens to Heidi yodeling around with the goats and all that kind of stuff? It's a big change in their national psyche. They're a snow-based economy. And they've already had big national conferences. What do we do when the snow is gone? So they're trying to be preemptive. Talking across these different scientific groups, we've begun to form these kind of networks. We've joined with 5 other areas in a USGS consortium to better marshal our forces, leverage our knowledge. And we've also created these networks that are kind of cyber networks, but we have these really neat meetings every other year that simply are exchanges of scientific information. And sure enough, you know, tree lines don't respond the same way in the Sierras as they do in Glacier Park. And we need to have those kind of more explicitly known. Let's see. We also, at Glacier National Park, have started to tell the story. In the past, it was like, yeah, it's happening. But now it's actively part of the education outreach that the park is mandated to do to the American people. And so we have a variety of things, brochures and talking points and things like that. And when you drive the Going to the Sun Road this year, you can look at this brand spanking new roadside exhibit that talks about climate change and looks at the glacier in the background and interprets that. So this is important just so that we're all on the same page informationally. Outreach is important. You need to tell these stories, and a lot of these stories are not being told effectively or often enough. We can also begin things that probably should have been doing anyway. In this particular case at Glacier Park, they've started shuttles. They've converted to biodiesel. They've been integrating climate change and its concerns into the management system. They ride bicycles to meetings instead of driving SUVs. You know, so there's a whole host of things that you can do right away that are being done. And of course, these charismatic antique buses are really not antique other than the metal on the outside. Underneath, they're a modern engineering marvel, very energy efficient, running on propane. So we can disguise how good we are sometimes. The big heavy machinery that clears the Sun Road, you know, there's a lot of biodiesel now. And so it's simply becoming part of the language and part of the way that management is considered. And the last thing is that, in a way, as you look at the shuttle system that now is reducing traffic on the road, allowing people to get to hikes and so forth, it's not only good environmentally, but of course it solves a lot of other management problems too, like traffic jams. And one thing that we often don't consider, and it sounds like you're going to do this in your next lecture, where you're reducing the carbon impact by having a cyber seminar here, information is very, very good for the environment and is very, very good for combating climate change. And these are part of the intelligent information system where simply by logging in on these different points, you can find out if the parking lot's full or the campgrounds are full, and you can change your plans on the fly. At least that's the concept that they're looking at. So information and better use of it is clearly one of the first steps we can take. So I think that with kinds of changes going on in the crown of the continent, and that mirror basically changes over most of the globe, you know, we have to better understand how those are impacting our resources, try to get a better handle on what's coming around the corner. But there are a lot of things that we can begin doing right now, and I think this is the the mandate that we all have as we live in the crown of the continent ecosystem. So thank you very much. So I'll take a few questions here before you're let out for recess. Yes?
Is your research budget going up, down, or staying neutral?
The question is my research budget going up, down, or stay neutral? And quite frankly, the answer is yes to all of those, because it looks like some of those graphs I showed where it's variable, it goes up, and then it crashes. So without being too facetious about it, it has been pretty bleak in the last few years, and we're now starting to see some pretty substantial initiatives to increase it again, as I think Congress in particular, the funding agency for our country, is taking this quite seriously. And so I think that in the next couple of years you'll see a lot greater push. Interestingly, the emphasis in the past has been, is it real? How fast is it going? What kinds of problems is it going to cause? A lot more of the new funds are going to be directed towards what are we going to do, and let's get after it. So I think you're starting to see a shift, and this isn't my opinion, it's just reflected in the bills that you see getting put before the floors of both houses, that there is definitely a drive to start doing something. Yes?
What's Glacier doing generally to help scientists become better storytellers?
Well, scientists generally are lousy storytellers. And that's something that actually I'm part of a committee with the AGU, American Geophysical Union, and we're looking at creating skill sets for scientists to tell their stories more compellingly. And one of the problems in science is that you never believe anything 100%. You believe it 95%, you believe it 99%, so you couch everything in terms of these caveats. Well, that's not the way most people's brains work. They want to know, is it happening or not? And they want, confident answers. And this is very hard to break scientists of. So there are a lot of initiatives now to try to get scientists to use visual techniques and put things on YouTube and things like that where people actually hear them. Because a really well-crafted message that nobody hears is really not worth anything at all. The Park Service, Glacier Park in particular, has sort of embraced this with their Crown of the Continent Research Learning Center. And they're dedicated to being a bridge between the science information and making it into the kinds of stories that people listen to. And so they've done a great service in getting science to be part of the way that people view Glacier National Park. So they're experimenting with different kinds of venues, and they're trying to train us scientists too. Yes?
I heard a recent report that plants and trees were not taking up as much carbon, or the carbon they're taking up wasn't having the predicted effect on carbon levels overall. And I was wondering if you could tell what you know about that and how that might be affecting this area with glaciers.
Okay, the question is whether plants and trees in particular are absorbing the kind of carbon dioxide that had previously been predicted, and how that basically plays out here in the Northern Rockies. It's a very complicated counting system. The first thing is that we know that the boreal forests, which we hoped would be a huge carbon sink, are not. Because as you know, plants they take in carbon and they also release carbon depending on the species, where they're growing, and of course their age. And at some point, the absorption of carbon and the respiration are such that you basically have a neutral balance for that particular tree at that particular size and age. So you have to look at the dynamic. Now when they're sitting there, they're still holding that carbon. And so one of the things that is often overlooked in the media is that land use change is at least as large an input to carbon dioxide in the atmosphere as is burning fossil fuel. It's not all about just energy and our use of that, but how we deal with landscape changes are very important. And that includes things like how we manage fires, because fires release a lot of carbon dioxide when they go up, and it's a complicated accounting system to find out whether the vegetation that replaces that, which is very aggressive about sopping up the carbon dioxide, more than replaces what was released in the burn in the first place. So without going into too much more detail, what I hope I'm conveying is that it's very, very specific to very different kinds of forests in different climatic areas as to whether it's a net benefit or not. As you probably know, there was a lot of impetus to just plant trees everywhere. And it would be nice if that was all it took. But unfortunately, the interaction between carbon dioxide and vegetation on this planet is a little bit more complicated than that. They found, for instance, that lab results did not play out in the field where the curve of absorbing carbon was not as great as they thought it would be. So we have a lot to learn about that still. But the key thing we know is that releasing more is not part of the solution. Whether vegetation can be aggressively managed to help resolve the carbon dioxide problem is, I think, the answer is yes in some places, no in some places, and then there's a lot of big places where it's still maybe. So that's about where the state of the art is. Yes?
You, of all people, know that the ball is definitely rolling and we've crossed so many thresholds. Do you really foresee, as a scientist, us being able to backtrack a bit or to put on the brakes? And if not, how do you see us and the ecosystems adapting?
A lot of the thresholds that we've crossed, I'm not sure that we can go back on. Some of them are quite major, and I think that we have to adapt to basically the new regime. One of the definitions of a threshold is that it doesn't go back, at least not without some active intervention. So I think that your question's a little abstract, but I would say basically in most cases our efforts are better placed in figuring out how we're going to use that new regime that we're finding ourselves in and try to prevent crossings of further thresholds. The difficulty is that when you cross one threshold, as I hope I showed, you can have cascading effects on other parts of a system. And I think having some knowledge of that will allow us to perhaps move to those other parts of the system and prevent threshold crossings there. But I say it like we know where the thresholds are and even what they are, and the reality is actually a lot more complicated. So I'm hopeful that as we understand ecosystem functions better, we'll be able to give more specific answers. One of the silver linings to the whole climate change urgency is we're learning more about how our planet works than we ever did before, because now we have to. And so we understand a lot more about planetary dynamics than we did 10 years ago. So that's one of the bright spots of all this. Yes?
You said that all the glaciers in Glacier National Park would be gone by 2030. So what would we have to do, or is there any way that we could stop that from happening right now? I mean, that's not very long and very far in the future. So.
No, the question was the glaciers will be gone by 2030. Is there anything we can do to stop that? Dismally, no. There's nothing we can do to stop these glaciers from going. On a planet-wide basis, most of the mountain glaciers are pretty vulnerable. We would have to have a really major cool down to start getting them back. In some cases, climate change paradoxically has at least temporarily increased the size of some glaciers because a glacier is just a checkbook balance between how much snow gets and how much melts with temperatures, and then there are some other drivers that are important too, but those are the two main ones. And in some areas, the warming of the ocean has brought so much extra moisture on land, but it was still cold enough to be snow, that they actually built up for a while. And those have now been, to my knowledge, all reversed. There are glaciers that are spreading out and appear to be growing, but their mass is actually shrinking. They're thinning out. And I'm sure there are a few glaciers somewhere that are growing, but the vast majority of them are disappearing fairly quickly like ours. It's just that ours started off a lot smaller and perhaps were more vulnerable, so they're sort of ahead of the crowd. but even the glaciers in the North Cascades, which are very, very large compared to ours, are all showing the same kinds of melt. So there's nothing we can do in the short run, but glaciers have disappeared and come back in the past. So with a little planet management, they can come back eventually. So yeah, I'll take one more question. Yes?
Do we in the United States have enough scientists and intellectual pool to solve the problem?
The question is, do we have enough scientists and enough intellectual pool to solve the climate change problem? Well, of course, there's never enough scientists. But notwithstanding that, I would say, yeah. I mean, I do think that we have a very strong science infrastructure in this country still. I think that we are leveraging our science impact by collaborating with scientists around the world more effectively than at any other time in the past. So I would almost rephrase that and say that I think we have a global pool of scientists that can solve the problem, but some problems are intractable, some just take a little longer. And I think this is one that will take a little longer, but if you are like me, trying to keep up with all the latest developments and the massive amount of literature, I mean, it's a tsunami of information. We have so much now that processing is almost going to be as much of a problem as anything else. So, no, I think the pool is there. The hard part, as I think one of the earlier questions alluded to, is communicating that effectively, distilling it to its essential elements, and getting the information to the politicians, the decision makers, the landscape managers, so that they have the best information to make the best decisions possible. So, thank you. I'll stay here a few minutes if anybody has individual questions, but I thank you for your attention. Oh, you bet. All right, good, good.